Okay, so this is the physics review. I'm using my home laptop, so hopefully everything will work out. Got my other computer working on something else. So let's just go through kind of a review of what we've done. The first thing we did was we looked at forces on moving charges. And there were a couple of variations of that. We had just the force on a moving charge. So what you have is you have a charge. Say we have a positive charge that's moving from left to right or right to left. So that's the velocity of the charge. And there's a magnetic field that say, we're going to show that by these little dots, which means that it's coming out of the paper. So there's the magnetic field strength, there's velocity, and there's the charge. So there's some charge Q in coulombs. A lot of times these are, electrons or small charges. And so there's going to be a force acting on this charge because it's moving in the presence of a magnetic field. What's really happening is the charged particle, as it moves, creates a magnetic field around it, which interacts with this external magnetic field. And the value for the force is equal to the product of the charge times the velocity, meters per second, times the magnetic field strength. And then you multiply it by the either the sine or the cosine. And what we have is you have the angle, basically, if we're looking at from the top vertically. So here's the velocity, and then this is the magnetic field. Let's say it's pointing out, it's pointing down instead of up. So that's the magnetic field, and this is the angle theta between the two. And you get the maximum effect of this interaction when they're perpendicular to each other. And the force is going to be perpendicular to these two vectors. So in this case, it's coming out or in or out of the screen here because the magnetic field is coming either in or out. It's going to be up or down. So because of that, it's going to be the cosine of theta. Now, for most of the cases that we have, this angle's 90 degrees. And that's what's happening up here. You've got the velocity going this direction, and you've got the magnetic field coming out, which is going to be 90 degrees. So you get the cosine of, actually it must be the sine, because cosine of 0 is, cosine of 90 is 0, so it's actually the sine of theta. So when theta is equal to 90 degrees, sine of theta is 1. So you get the maximum effect. So most of the cases that we've looked at, that's going to be 1. And so the force is just the product of these three things. To make sure that the charge, if I give you the charge in microcoulombs or some really small charge, something other than just coulombs, you've got to convert it. The velocity has to be in meters per second, and the magnetic field strength has to be in Tesla. So if it's in millitesla, you'd multiply, if it's millitesla, so you have 10 millitesla, that would be 10 times 10 to the minus 3 Tesla. If you had 20 microtesla, that would be 20 times 10 to the minus 6 Tesla. So you've got to convert them to Tesla, like this. So to calculate the force is pretty simple. You just multiply it together. Multiply those three things together. Now, remember there's a couple of right-hand rules. This right-hand rule is fingers in direction of velocity. And this all applies for a positive charge. So if it's a negative charge, it's it's the opposite direction. So for a positive charge, you put fingers in the direction of velocity, curl, then curl fingers in direction of magnetic field. Thumb is the direction of force. So for this particular example, so take your right hand, put your hand in the direction of velocity. Now if I had little crosses, the magnetic field would be going into the board, and I'd curl my fingers in towards the screen, and my thumb would go up. But in this case, I have to go the other direction, so I'm going to turn my hand upside down. So my fingers are going to go in the direction of velocity. I'm going to curl my fingers out of the screen, towards out the screen. My thumb goes down. So for this particular example, the force is going to go down. And there are, I think, basically maybe 8 combinations. You know, you can have velocity going from left to right or right to left. So if it was going, the velocity went the other direction, the force would go up. If the velocity is going the same direction, but the magnetic field strength is going into the magnetic field is going into the board, then it's going to go up. And again, if this were a positive charge, negative charge, it would be going up. So if you change any of the direction of the magnetic field, the direction of velocity, or the charge, if it's negative instead of positive, things are going to change. So you just got to think about all those different possibilities. So I'm going to ask you, which direction you're going to. It's either going to go up or down. You got a 50% chance. Okay. Now, the next thing is if you put all those if you put the charges in a wire. So the force on a wire in a magnetic field. What is it? So that's the question. Well, force is equal to, well, instead of, if we go back to the previous one, we had velocity. Well, we're not going to measure velocity in a wire, but we are going to measure current. And we're going to measure magnetic field. And the only other thing we have is the length of the wire. So if you've got a wire, and here's the current flowing through the wire. So the current's going this way. And let's say the magnetic field is going into the board this time, into the screen. Like that. And then you also have the sine of theta, where theta is the angle between the direction of the current and the direction of the magnetic field. Again, most of the time we're going to simplify it down to where theta is equal to 90 degrees, and you'll get the sine of 90, which is 1. So typically it's just these 3 terms. So where L is the length. So when you're doing these cheat sheets, you want to make sure you do the equations, but you're very explicit about what the units are for each one. So again, you have the right hand rule, and because the current is the direction of positive charge flow, you don't have to worry about this positive versus negative, because the current is always positive. Charge is going this way. So if we use the same right hand rule. So if you take your hand, point it in the direction of the current, your flat hand, and curl in towards the board in this case, because I've got little X's. That's the tail of the arrow. So I curl my hands in towards the board, and my thumb goes up. So in this case, the force direction on the wire is upward. Now if the current went the other direction, the force would be down. If the current was going the same direction but it went out of the board, then the force would be down. We don't have to worry about the third case, which is whether you are dealing with positive or negative charges, because it's kind of default. And if you take a current and you create a loop of some kind, it doesn't have to be square. So the current goes in here and then goes around the loop, and this thing is rotating around some axis. And this has some dimension, let's say A, and this has some dimension B on this axis. Instead of looking at the force for this, because you're rotating around an axis, the maximum torque is going to be equal to the current times the magnetic field times the area. And how did I know that? Well, torque is force acting through a distance. So this is going to have units of meters and newtons. Up here, force was just newtons. Okay. So if you have meters and newtons, you'd have to multiply unit-wise by meters. So that would make I'd have an extra length unit compared to this. So instead of having length, I have area. And I have the other stuff. Now, you actually get the maximum torque when the thing is oriented like this, where it be rotated 90 degrees. So at this point, the forces would be going like that, and you wouldn't get any torque. It would be when it would be rotated. So, but it's hard to show this area when it's going into the board, so that's why we do it in that sense. Okay. So, I don't know why I wrote that down there. So that's the maximum torque. Now we're not worried about the direction. So if I give you a current loop, and I can tell you how much current's flowing through the loop, what the magnetic field strength is, and if you can calculate the area, then you can calculate the maximum torque. And the area doesn't depend upon being square. So if I had a circular loop, you just take the area of the circle. So again, write down in your paper, A is area, it has to have units of meters squared. I is the current. It has to have units of amps. So if I give you milliamps, you'd have to convert that. Area, I already did that. B, that's a magnetic field strength. Now in a motor, what we do is we have a split ring at the end. So what happens halfway through the rotation, the current changes direction. And what that'll do is it'll keep the thing moving around in a circle. Now there's also the force between two wires, which is an interesting thing, but there's not a whole lot of practical use for that, except maybe for defining the current. So those are the forces on charged particles, whether they are charged particles going through space or whether they're charged particles that are contained in a wire. The second thing we looked at was, what is the magnetic field generated using from a current, for flowing current. So we had three cases we looked at. We looked at the magnetic field around a wire. Remember what we had is, here's the wire going in, and you had magnetic field lines that went around this. And there's a distance from the center of the wire to some point in space. And let's say the current I is in towards the screen. So if you take the way the right hand roll in this case, you take your hand, you push your thumb in towards the screen, and then you curl your hands around. So if the current is going into the screen, then the magnetic field is rotating, going around clockwise. And if it's coming out of the screen, then it's going to be going counterclockwise. So I is in toward the screen. The magnetic field is clockwise. So that's the right-hand rule. And the equation, if I remember correctly, is the magnetic field strength at any point in space is equal to mu0, which is the constant associated with magnetism, times the current divided by 2 and the radius. I'm going to just double check that. I don't think there's a pi involved. And remember, that came from using, I don't know how those units came in there. That thing. Okay, so I'm just looking at chapter 19 in the, not in your book, but in the other book. Okay, so it actually does have 2 pi in there. This was derived using Ampere's law, which is one of the 4 laws of what's his name? Faraday, of course, but also we were talking about it the other day. James Clerk Maxwell. So again, if I gave you a current and I gave you the distance from the wire, and you have mu0, which I'm going to write this down on a piece of paper. So this is called, I always forget the names of these things. It's called the permeability of free space, and it's equal to 1.26 times 10 to the minus 6th. And the units you can figure out, it's going to be Tesla from there, and meters from R divided by current, which is amps. So it's Tesla meters per amp. So that's pretty easy. Then you have a loop of wire, or loop of wires. So what that is, remember in class we had that loop, and so there's a radius to the loop, and some current flowing around the loop, and they're in turns. So what happens is each loop is going to add on to the amount of magnetic field inside. So the more loops you have, the greater the magnetic field strength. And the equation there is for a loop. It says the magnetic field strength at the center of the loop is going to be equal to n number of loops times mu0 times the current divided by 2r. So we don't have the pi, we get n. And so depending upon the direction of the current, it's either going to loop around this way or it's loop around that way. So that's Lenz's law. Actually, it's not Lenz's law, it's just the law. What you do is you take your finger again, your right hand, put your hand in the direction of the current. Put your thumb in the direction of the current, and then the direction your fingers would loop around. So what I would have in this case is I would have the magnetic field coming out from the loop, and it would be going in outside the loop. So I'd have my if you take your thumb and you put it in the direction of the current, which is going counterclockwise. My fingers are going to loop around that thing, and my fingers are going to come out and point towards me on the outside. So that means it's coming out inside the loop, and it's has to go in. So it kind of goes back like this behind the loop, comes back out this way, and then it loops around in front of that wire. Again, make sure an N is the number of turns. There's really the dimension of the loop in towards the board is negligible compared to the radius of the loop. Now, as we did in class, we saw that if we move our magnetic field sensor, it does actually get a higher strength here at the edge, and I'm sure you could use calculus to do that. I think Ampere's law was used. Same thing that was used over here you can use for this loop to come up with this result. And then the final thing was for a solenoid. And again, so what a solenoid looks like is you got like this tube that has a length to it. So this is the length of the solenoid. And what you have instead of loops, you have loops per length. So this would be the number of loops, this would be the length. N is the number of loops per length. And what happens is the magnetic field strength inside the solenoid all the way through it is constant. So it's constant this direction, it's constant everywhere. And that applies if the diameter of the loop is much smaller than the length. So the diameter or the radius of the loop doesn't come into play. And so the magnetic field strength inside that solenoid is equal to mu0 times the number of loops per length times the current. So that's for a solenoid. So those are the three ways we've done all of these, except for the first one. We didn't measure the magnetic field around a wire because it's usually pretty small, but we stuck the magnetic field sensor in the middle here, and we measured it, and we changed the current going different directions in it. We were able to see that. And the second one is, trying to figure out how to do this to the thing. Right? A solenoid, we also put the magnetic field sensor in there. Remember, one other thing too is that this magnetic field strength, this is when you have just a hollow solenoid. If you put a metal core in there, that magnetic field strength is going to get significantly higher. We don't really have anything, we didn't talk about it at least. So all of this stuff, the magnetic field around a wire, the magnetic field in a solenoid, in a loop, these are all just pretty simple calculations. Plug and chug. You just got to know the rules, the right-hand rule. We didn't have one for a solenoid. I'm sure we could come up with, I guess, the current would go, if the current's going this direction, which would be, depending upon which way you're looking at it from. If you're looking from this direction, it would be counterclockwise. Then, if you take your fingers, you would, so if this thing's going counterclockwise around this tube, the current, then it looks like, put your fingers in the direction, put your thumb in the direction of the current, and the loop, and it looks like the magnetic field strength is going this way. Okay, so that was pretty much chapter 19, just the forces on moving charges due to magnetic field and the magnetic field created by moving charges. Chapter 20 talked about Faraday's law. And Lenz's law. Now, Lenz's law was which direction does the induced current happen? in a loop, which is hard to do on a test, so we talked about that enough in class. Now, Faraday's law says that the electromotive force, which is the voltage, is equal to the number of turns times the number of turns in the loop. So these are all induced currents in a loop of some kind, whether it's a solenoid or just a loop of wire or just a single loop. And make sure I have the sign correct here. There's a negative sign. But really, Lenz's law is the one that tells us what direction. And what you have is the rate of change of the magnetic flux with respect to time. Now, if you just have 2 points in time, you could say delta phi over delta t instead of d phi dt. And since this is not calculus-based physics, we're going to use the second one. And the magnetic flux is equal to the product of the magnetic field times the area through which that magnetic field is going. So remember, we had our hula hoop, and we had the magnetic field going through that somehow or another. And what we're looking for is the rate of change of that. So we did that by, say, moving a magnet in and out of the loop. Also, if we had say a coil inside here, and that was time varying in time because of the varying current in the solenoid, we also generated a time varying current around the loop. So we have a changing magnetic flux, and the magnetic flux is the magnetic field strength times the area. And you'd also have an angle between the flux lines and the area. How you define the area. The area would be associated with this hoop would be perpendicular to the hoop. So in this case, it turns out it's the cosine of theta, or cosine of whatever this, however we define this angle. Let's say we can't use phi because we've just used phi, so let's say theta. So when the area surface is perpendicular to the magnetic field lines, the actual vector associated with the hoop as they're parallel to the magnetic field lines, and so that's an angle of 0, and you get the maximum effect, maximum magnetic flux. So how are we going to have a test problem on this? Well, what I'm going to do is there's going to be like a start time, and there's going to be an end time. And you're going to have some phi initial, or actually what you may have is some magnetic, like some initial value of the magnetic field. And you're going to have some final value of the magnetic field. And then there's probably some area associated with it. We won't change the area. So the change in magnetic flux is just going to be equal to the final magnetic field strength times the area. That's the final magnetic flux minus the initial magnetic field strength times the area. So that gives you the delta phi, and there's some time over which this change occurs, so that's t. So delta phi over delta t is just going to be equal to the numerator, which is the change in magnetic flux divided by the time it takes to make that change. So that gives you d phi dt, and therefore the voltage, and this is an average voltage generated during that time period, it's just going to be the negative times the number of loops in the problem description times the final magnetic field strength times the area minus the initial magnetic field strength times the area over t. Now, what about signs? Well, again, Lenz's law ultimately would tell us which direction this is going. So we're kind of not going to worry too much about the signs. You just have to do this calculation. Again, make sure that magnetic field strength is in Tesla. area is in meters squared, time is in seconds, loops is in loops. And then you can estimate you can estimate the average voltage during that time period. Okay. Just looking through my stuff here. Now the area, if it's a circle, the area will be the area of a circle, 2 pi r squared. If it's a square, then it'll be the height times the width. So you should know how to do those things. So that's all I'm asking you. What you ultimately should remember in the long term is that a changing magnetic flux is going to induce a voltage in a loop of wire that is in the direction according to Lenz's law. So remember, Lenz's law says that you're basically trying to maintain the status quo. We did that with those fake magnets in class. So we wanted to, as say the magnetic field, the pole that's moving towards or away from the loop, you want to keep the moving magnet from either getting away or coming. You want to keep it where it is. So if it's moving, you put the same pole towards it. If it's moving away, you use the opposite pole to keep it from going. And then that magnet, the north to the south pole, is the way that you want the current to flow in the loop, so that it results, using the right-hand rule, results in a magnetic field that's in the proper direction. So again, what do you need to know? Well, what I hope that you would know when you leave the class is that there's this law, Lenz's law, that tells you that which direction the current flows depends upon the direction of the change in the magnetic flux, or something along those lines. But for the test, just know how to calculate it between 2 time periods. Now, in the same chapter, chapter 20, we introduced self-inductance, and what we said was that if you have an inductor, which is just a coil, so which we've been using a solenoid in our class, this has some inductance L. And it turns out the voltage across an inductor is equal to the inductance times the derivative of the current with respect to time. And it comes from Faraday's law. This is voltage, except it's EMF, which means it's just being generated. It's a voltage that's being generated externally, in this case because of the changing magnetic field. The N, the area, kind of go into the L term, the inductance. The magnetic field is associated with the current term. But the bottom line is, this is just an additional electrical element in your circuit: resistance, capacitance, inductance. And we derived in class that the voltage across an inductor is a function of time for an RL circuit. So you've got a resistor in here, and then you've got some voltage, and you go from 0 voltage to some voltage. The voltage across the inductor is going to be equal to the input voltage times E to the minus R over L times T. So when T equals 0, this goes to 1, and you have initially all of the voltages across the inductor, and there's no voltage across the resistor. The voltage across the resistor is equal to the input voltage, which is this voltage right here due to the battery, the DC source, times 1 minus E the minus R over L T. So if I plotted the voltage across the inductor, it would look, as a function of time, would look like this, exponential decay, and this would be the input voltage, and then it decays to 0. For the resistor, it looks like this, with it approaching the input voltage. And if I add these two together, I get the input voltage. So the sum of these two curves always equals the input voltage. And then the current, which is the same for each element, because the current can't go anywhere, it has to go through each part. The current as a function of time is equal to the voltage divided by the inductance times, which one of these is it? It's 1 minus e to the minus r over L T. So that comes back, if I go back to the definition of inductance, oh, that's right here. Voltage equals inductance times the derivative of the current. So the current is going to be unit-wise is going to be the voltage divided by the inductance. There's this time thing in here, so what is that? I guess that, I think the units are okay. Just thinking about units. Seems like I have a T in there, but I don't think I do. Let me just check the equation, see if there's, they wrote something here. I'm sure they had that in the book. RL circuits. Current is V over R. Actually, it's V over R. That's why it didn't work. So it's V in over R, not V in over L. So the current from Ohm's law, voltage is equal current times resistance. So that's why I was confused, because L wasn't going to work. So the current is a function of time, and that's the current through the resistor and the inductor is this. So it starts off when you have t equals 0, you get e to the 0, which is 1. So the current initially is 0, and then it increases to the final value. So if I plotted current as a function of time, what it would do is it would look just like the same shape, except instead of here it approaches the input voltage, here it approaches the input voltage divided by the resistance, which is their steady state current. And it'd be the same current that goes through this resistor. If you didn't have the inductor, it would just go immediately, it would go boom straight up to that current. But because of the inductor, what happens is this inductor makes it so the current can't change infinitely fast. It slows down the current change, but it ultimately does. In the end of the day, this current through the inductor becomes constant, and a current through an inductor creates a magnetic field, but it doesn't create a changing magnetic field, so it doesn't induce anything. So it just becomes basically a wire. So make sure if I give you times, be able to calculate the three things there. Okay, what else? RLC circuits. So we've done a lot of those. Take those examples in class, and so what you're given is you're given a resistance, which is the resistive reactance you have. So that's just equal to that. It's the inductive reactance is 2 pi times the frequency in hertz times the inductance. That's an X, and X sub C, sorry. That's the capacitor is equal to 1 over 2 pi F C. So you get these numbers, and they're in ohms. These all have units of ohms. From that, you can calculate the impedance, which is just looking at basically the hypotenuse of a right triangle. So you have x sub r squared plus x sub l squared minus x, no, I gotta take the difference and then square it. So it's x sub l minus x sub c squared, that's an L. So that gives you an impedance, which is also in ohms. And from that, you can relate the maximum voltage. So the maximum voltage is going to be equal to the you gotta be careful, because there, it's not going to be Z times I max. You've got to take into account the phase angle difference. So let's make sure we get all this correct. So just want to back a chapter. Actually, it does work out okay when it comes to the maximum values. So the maximum voltage is Z times the maximum current, or the maximum current is equal to the maximum voltage divided by Z. So depending upon which one of these I give you, you can calculate that. The phase angle is equal to the inverse tangent of x sub L minus x sub C divided by x sub R. And this phi tells us whether the current lags or leads the voltage. The RMS current is equal to the maximum current divided by the square root of 2. The RMS voltage is equal to the maximum voltage divided by the square root of 2. And we use RMS when we're calculating power in a AC circuit. So if we use a voltmeter, we measure RMS current and RMS voltage, and to calculate power we could use the appropriate relationship. So the power is equal to the RMS voltage squared times the resistance, or the power is equal to the RMS current times the RMS voltage times the cosine of the phase angle. So either one of these work. So again, kind of summarize what we've done in those handouts. Everybody seemed to do pretty good on that. Then we have transformers. So transformers, what you have is you have a primary loop. Transformers only work for alternating current. So you're going to have N1 loops, and then you have a secondary which may have more or less loops, or you could actually have the same loop, but that's called an isolation transformer. So this has N2, which in this case is more, but it doesn't matter. When we call this the primary side, and this is the secondary side of the transformer. And what happens is, you've got some time varying signal coming in, some frequency. Frequency is not important, just so that it's great enough to create a changing magnetic field. So what's going to happen is you're going to come out with on the other side of the transformer, you're going to come out with the same frequency, but it's going to change in magnitude. And so what happens is you have this iron cord that connects these two, like that. And so you get this magnetic flux that's flowing through both cores. This one's, you're creating the magnetic flux change. In this one, you're inducing a changing voltage in the second core. And basically what you have is this relationship that the voltage in the secondary loop is equal to the voltage in the primary loop. And it's either N1 over N2 or N2 over N1. So when you have more loops in N2 than 1, you're going to increase the voltage. So it's going to be N2 over N1. And the voltage it applies to maximum voltage, but in this kind of situation, you're really more interested in RMS voltages. That's what you would measure with your voltmeter, and that's what would be important as far as power transmission. So I'm going to put RMSs in there. So you get N2 over N1. So I'm just going to double check. Make sure I got right. Yep. Okay. Now the second thing is, nothing's for free. So when you look at power, the amount of power that goes into the transformer, it has to be the same or less that goes out of the transformer. So if we assume an ideal transformer, we're going to assume the power is conserved, the energy is conserved. So power, remember, is equal to voltage, current times voltage. So what we have is we're going to have that I1, the current in the primary loop, times the voltage in the primary loop is equal to the current in the secondary loop times the voltage in the secondary loop. So let's say if you have what's called a step-up transformer, then N2 is going to be greater than N1, so therefore V2 is going to be greater than V1, so I2 is going to be less than I1. So if you increase the voltage, you have to reduce the current. If you have a step down transformer, what happens there is N2 is going to be less than N1. That means V2 is going to be less than V1, and therefore I2 is going to be greater than I1. So this is the case of the transformer that's going from the wall to your computer. You're going to lower the voltage, but the current can increase across the transformer. So these are the two relationships. And again, these would be RMS values. RMS. Now you don't have to worry about phase angle or anything like that. That doesn't come into play. And the final thing relates to electromagnetic waves. And the only thing I want you to be able to do is to relate frequency to wavelength. So what do we know? But this is about in waves in general. But it also, in this case, it's electromagnetic waves, which can be radio waves and whatever that song is. So we know that the speed of electromagnetic waves is 3.0 times 10 to the 8th meters per second. And the relationship between wavelength and frequency is that the wavelength is equal to the wave speed times the frequency. I think that's it. Let's double check it unit-wise. Wavelength is meters. Speed is meters per second. And frequency is cycles per second. So apparently that's not correct. So let's fix it. So how about speed is equal to frequency times wavelength? Let's try that one. It involves these three things, so let's look at the units. Again, I'm trying to minimize the stuff I have to remember. And I know speed is meters per second. I know frequency is 1/seconds. Okay, so let's check this out. Frequency is 1/seconds times wavelength, which is meters per second. Okay, so that's the relationship. So all you have to do for this problem is, I'm either going to give you lambda and you calculate f, or I'm going to give you f and you're going to calculate lambda. That's pretty much it. And this relationship applies to any waves that are moving in space. C may change. It may be the speed of sound or the speed of an actual string, but in this case, it's speed of light in a vacuum. So let's just do one example. Let's say if frequency equals 1.7 times 10 to the 10th power hertz, what is the wavelength? It's going to be really small. Wavelengths for light are really actually very long. Okay, is that right? No, depends. We'll just see, figure it out. Okay, so if I solve that equation for lambda, it's going to be c divided by f. So c is 3 times 10 to the 8th meters per second. Frequency is 1.7 times 10 to the 10th meters per second. So the wavelength, get my calculator. So 3e to the 8th divided by 1.7 e to the 10th. So I get 0.0176 meters. Okay. The other case is if the frequency, the wavelength is 5.7 meters. What is the frequency? So solve for f. In this case, f is c divided by lambda. So that's 3 times 10 to the 8th divided by 5.7 meters. This is meters per second. And actually up here, frequency is not meters per second. It's cycles per second. And again, cycles don't have units. So you get 3e to the 8th divided by 5.7. And so it's 5.26 times, I want you to put this in scientific notation, so 1, 2, 3, 4, 5, 6, 7. So it's 10 to the 7th hertz. So it would be 92.6 megahertz, because a mega is, besides my name, granddad name is 10 to the 6th. So if I take this and divide by 10 to the 6th, I'll get 92.6. So it's 92.6 megahertz. This one, originally 10 to the 10th would be, what's after mega? It's megabytes, gigabytes. Okay, yeah. So this would be 17 gigahertz. Giga is, then you have tera, right? Remember that for computers. In terms of storage size, you go mega to giga to tera. Okay, so that's pretty much it. There's really not, the tricky parts are just the right-hand rule. The rest of them is just plugging stuff in. So hopefully you all do well on that. Usually people do well on this thing.